Have you ever stared up at the night sky and felt that tug of curiosity, that quiet longing to understand what lies beyond? Out there, in the vast and silent darkness, some of the universe's most profound secrets are hidden secrets that challenge everything we think we know about space, time, and reality itself. And at the heart of this cosmic mystery, one phenomenon captivates and confounds us like no other: the black hole. These aren't just distant astronomical objects. They are portals to the extremes of physics, where gravity becomes so overwhelming that not even light can escape their pull. Black holes force us to rethink the very fabric of the cosmos. They warp space, slow down time, and may even hold clues to the origins of the universe itself. For centuries, human imagination has been captured by the unknown, but black holes take that sense of wonder to another level entirely. They are both terrifying and beautiful, destructive and creative, and they invite us to explore some of the most profound questions we can ask. What happens at the edge of existence? Could a black hole be a gateway to another universe? And what do these cosmic giants reveal about our own place in this vast, expanding reality? In this video, we're going to journey together into the heart of that mystery. We've gathered 30 astonishing facts about black holes, each one more mind-bending than the last, that will completely reshape how you see the universe. From their formation in the fiery death of massive stars to their role as cosmic architects shaping galaxies, these facts will take you from the familiar night sky into realms where physics as we know it begins to break down. This isn't just a list, it's an invitation to see the cosmos through new eyes, to marvel at its grandeur, and to reconnect with that childlike wonder we so often leave behind. So sit back, open your mind, and let's explore the unbelievable truths hidden within these dark celestial wonders. Let's start by clearing up one of the biggest misconceptions out there. The name itself is a bit of a trick. When we hear black hole, we naturally picture an empty pit, a dark tunnel, or a vacant void in space, but that couldn't be further from the truth. A black hole isn't an empty hole at all. In reality, it's the exact opposite. It's arguably the most full, the most densely packed thing in the entire universe. So what is it then? Imagine taking something incredibly massive, like a star at least 20 times bigger than our own sun, and squeezing it. Now squeeze it some more. Keep compressing all that immense mass until it's crushed down into a single point smaller than the tip of a pin. You've just created a black hole. This point is known as a singularity, a place where gravity is so intense that the laws of physics as we know them simply stop working. The density is beyond human comprehension. To put it in perspective, if you could somehow compress the entire Earth down to this density, it would be smaller than a marble. This unimaginable density creates a gravitational pull so powerful that nothing, not even the fastest thing in the universe, light itself, can move fast enough to escape its grip. And that's why it looks like a hole. We can't see the singularity itself because any light that travels toward it is swallowed forever. What we can define is the point of no return, the boundary around the singularity where the escape velocity exceeds the speed of light. This boundary is called the event horizon. Think of it as the ultimate one-way door. Cross that invisible line and there is no coming back, no sending a signal, no possible way to communicate with the universe outside. So while it appears to be a black sphere of nothingness, that darkness is actually a perfect silhouette, a shadow cast by the most extreme object nature has ever devised. It's not an empty hole, it's a cosmic trapdoor baited with the most irresistible force in existence, gravity. And that brings us to the engine at the very core of this cosmic trapdoor, the singularity. If the event horizon is the point of no return, the singularity is the reason why. This is the heart of the black hole, the final destination for anything that crosses the boundary. But to call it an object would be a profound understatement. The singularity isn't a solid ball of crushed star material you could theoretically touch. It's a point in space where the very concept of stuff loses all meaning. Imagine the entire colossal mass of that giant star, millions of times the mass of our own planet, compressed by its own unimaginable gravity. This force doesn't stop. It just keeps crushing, pulling everything inward with an irresistible violence until there is literally nowhere left for the atoms to go. All the protons, neutrons, and electrons are smashed together into a state of existence that our current laws of physics cannot describe. The result is a point of infinite density, not just incredibly high density, but truly infinite. It has zero volume, yet contains all that mass. This is the realm where mathematics as we know it fails, where the equations we use to understand the universe simply return error messages. At the singularity, the familiar rules of space and time cease to exist. The three dimensions of space and the one dimension of time, the very fabric of our reality, are warped beyond recognition. It's a place where the gravitational field becomes so intense that it theoretically curves to an infinite value. This is why physicists often say that inside a black hole, the roles of space and time actually swap. What was the inevitable forward march of time outside the event horizon becomes just another direction you can move in, like walking down a hallway, while the direction toward the singularity becomes as unavoidable as the passage of time itself. You don't fall toward the singularity, you are pulled into the future where the singularity is an inevitable event. This idea of a point of infinite density is so problematic that it's widely believed our current theories are incomplete. The singularity is seen not as a physical reality, but as a signal that Einstein's theory of general relativity, while incredibly powerful, reaches its limits here. To truly understand what happens at the center of a black hole, we would need a theory of quantum gravity, a way to marry the laws of the very large with the laws of the very small. The singularity is the universe's ultimate puzzle, a cosmic question mark reminding us that for all we've learned, the deepest secrets of existence are still waiting to be uncovered. But before you ever reach that mysterious singularity, you would experience something far more dramatic and visceral. A process so extreme it has a name that sounds like it's from a science fiction movie, spaghettification. It's a terrifyingly accurate description of what happens to any object unlucky enough to venture too close to a black hole's event horizon. The reason for this bizarre fate lies in the incredible difference in gravitational pull across your body, a phenomenon known as tidal forces. Here on Earth, we experience mild tidal forces from the moon's gravity. It's what gently pulls on our oceans to create high and low tides. But near a black hole, this force isn't gentle at all. It's violent and extreme. Imagine your falling feet first toward a stellar mass black hole. Your feet are closer to the black hole's center than your head is. Because gravity's strength increases dramatically with proximity, your feet feel a vastly stronger pull downward than your head does. This difference in force doesn't just gently tug you, it actively stretches you, pulling your feet away from your head at an accelerating rate. Simultaneously, your sides are experiencing something else entirely. As you're being stretched lengthwise, all the matter that makes up your body is also being squeezed inward toward the center line of your falling form. This is because everything is being pulled toward the single, central point of the black hole. So you are being both stretched into a long, thin strand and compressed from the sides, like dough being rolled through a cosmic pasta maker. This isn't a slow process either. For a smaller black hole with a more compact event horizon, the change in gravity over even a short distance like your height is immense. You would be transformed into a stream of subatomic particles in the blink of an eye. For a supermassive black hole like the one at the center of our galaxy, the event horizon is so large that the tidal forces at the boundary are weaker. You might actually cross the event horizon before being spaghettified, giving you a few fleeting, horrifying moments of conscious existence inside the black hole before the inevitable stretching begins. It's a stark reminder that in the presence of such raw power, the very structure of matter itself is no match for the unforgiving grip of gravity. Now that we've looked at the incredible forces at play around a black hole, you might be picturing them all as identical cosmic vacuum cleaners. But the universe loves variety, and black holes are no exception. They come in an astonishing range of sizes, from the relatively petite to the almost impossibly vast. The smallest ones might be just a few times heavier than our Sun, while the largest are so huge they defy easy comprehension, weighing in at billions of solar masses. This incredible size range isn't just a curiosity. It tells a story about how they form and the unique role each type plays in the cosmos. Let's start with the most common type, the stellar mass black hole. These are the remnants of massive stars that have lived fast and died young. When a star at least 20 times more massive than our Sun reaches the end of its life, it doesn't go quietly. It explodes in a spectacular supernova, blasting its outer layers back into space. What's left behind is the star's incredibly dense core. If this core is heavy enough, no known force can stop it from collapsing under its own immense gravity, and it shrinks down to form a black hole. These stellar mass black holes typically range from about 5 to 100 times the mass of our Sun. While that sounds enormous, their physical size, defined by their event horizon, is surprisingly compact. A black hole with 10 solar masses would have an event horizon only about 30 miles across. You could fly a spaceship around the entire point of no return in just a few minutes. On the opposite end of the spectrum, residing at the very heart of most galaxies, including our own Milky Way, lurk the true giants of the cosmos, supermassive black holes. These are not the products of a single star's death. They are cosmic monarchs with masses ranging from millions to billions of times that of our Sun. The one at the center of our galaxy, Sagittarius, a star, is a relatively calm example, weighing about 4 million solar masses. But others, like the famed first image from the Event Horizon Telescope, the black hole in galaxy M87, is a behemoth weighing 6.5 billion times more than our Sun. Their scale is almost impossible to grasp. The event horizon of such a monster would be so large it could easily encompass our entire solar system, stretching far beyond the orbit of Pluto. The existence of these giants presents one of astronomy's biggest puzzles. How did they get so big, so fast? We see evidence of supermassive black holes when the universe was very young, which doesn't give them enough time to grow solely by swallowing stars and gas. Astronomers have a few theories. They might have started as the first generation of incredibly massive stars that collapsed directly into large black holes. Or they could have grown through the rapid merger of many smaller black holes in the dense, chaotic environments of early galaxies. Some might have even feasted on enormous amounts of gas in the early universe, allowing them to balloon in size at an astonishing rate. Their powerful gravity doesn't just destroy, it also creates order, shaping the entire galaxy around them and influencing the birth of new stars, proving that even the most destructive forces in the universe can also be creative. But if you thought these supermassive black holes were just passive residents at the galactic center, think again. Their influence is anything but subtle. They are the unseen architects, the gravitational monarchs that rule their kingdoms with an invisible fist. It turns out that nearly every large galaxy we've observed, including our own Milky Way, hosts one of these colossal entities at its very heart. This isn't a mere coincidence, it's a fundamental relationship that suggests the black hole and the galaxy itself grow and evolve together in a complex cosmic dance. The sheer gravity of a supermassive black hole dictates the motion of stars swirling around the galactic center. Hundreds of stars orbit Sagittarius, a star, some whipping around at speeds of thousands of miles per second. their frantic dance a direct response to the immense pull of the 4 million solar mass object they cannot see. This gravitational dominance doesn't just affect the inner stars, it shapes the entire structure of the galaxy. Think of it as the anchor of the system, the central weight around which the vast, spinning disk of stars, gas, and dust organizes itself. Without this central anchor, a galaxy might not be able to maintain its elegant spiral form, and could instead be a far more chaotic and disorganized collection of stars. Perhaps even more fascinating is the role these black holes play in galactic evolution through their incredibly active phases. When vast amounts of gas and dust fall toward the event horizon, they don't just vanish quietly. This material forms a superheated, swirling structure called an accretion disk, which rotates at near light speed, creating immense friction and temperatures reaching millions of degrees. This process doesn't just create the brightest light shows in the universe, known as quasars. It also generates powerful outflows of energy and matter, blasting radiation and particle jets across hundreds of thousands of light years. This incredible feedback mechanism acts as a cosmic thermostat. These energetic outbursts can heat up surrounding gas, preventing it from cooling down and collapsing to form new stars. In this way, a supermassive black hole can actually put a limit on the growth of its own galaxy, effectively deciding when star formation must end. It's a destructive act that paradoxically leads to structure and order, preventing the galaxy from growing too large too fast. The presence and activity of the central black hole are therefore woven into the very life story of the galaxy it calls home, from its fiery birth to its eventual quiet maturity. For decades, the defining feature of a black hole was its absolute nature, a perfect one-way street where things go in, but nothing, not a single shred of information or particle of light ever comes out. This idea was a cornerstone of classical physics, but then, in the 1970s, a brilliant physicist named Stephen Hawking made a discovery so profound it turned this entire concept on its head. By applying the strange rules of quantum mechanics to the vast scale of black holes, he revealed that they are not the eternal prisons we once thought they were. In fact, according to his theory, black holes can slowly leak energy and fade away. This revolutionary process is called Hawking radiation, and to understand how it works, we have to venture into the bizarre, frothy nature of empty space itself. Thanks to quantum mechanics, we know that a perfect vacuum isn't really empty. Instead, it's a seething, bubbling sea of virtual particles. These are pairs of particles and antiparticles that spontaneously pop into existence everywhere, all the time, borrowing energy from the universe for an impossibly brief moment before they inevitably collide and annihilate each other, paying back the energy loan and vanishing without a trace. This is constantly happening all around you, a ghostly dance of creation and destruction that we normally never notice. Now, picture this quantum activity happening right at the very edge of a black hole's event horizon. One of these virtual particle pairs appears. In most of the universe, they would meet their end immediately. But here, at the precipice, something different can occur. One particle of the pair might fall just across the event horizon, while its partner manages to escape outward into space. The particle that falls in is effectively lost, but the one that escapes becomes real. It can no longer annihilate with its partner to repay the energy debt to the universe. To balance the cosmic books, the energy to make this escaped particle real has to come from somewhere. That energy is stolen from the black hole itself. From the perspective of someone watching from afar, it looks as if the black hole has just emitted a particle of radiation. This is Hawking radiation, and because the black hole is losing mass energy with every particle that escapes, it is very, very slowly evaporating. The smaller the black hole, the stronger the curvature of space at its event horizon, and the more intense this particle pair production becomes. This means smaller black holes actually evaporate much faster than their gigantic supermassive cousins. For a stellar mass black hole, the process is incredibly slow. taking many times the current age of the universe to evaporate significantly. But for a truly tiny, primordial black hole that might have formed in the early universe, its final moments could be happening right now, ending not with a whimper, but with a spectacular burst of energy equivalent to 1,000,000 1-megaton hydrogen bombs. Hawking's insight beautifully merged the worlds of the very large and the very small, proving that even the darkest objects in the cosmos are not immune to the subtle, persistent laws of quantum physics. This invisible boundary, the event horizon, is arguably the most significant frontier in all of physics. It's not a physical surface, not a solid wall you could bump into. Instead, think of it as the ultimate point of no return, a spherical boundary in space drawn by gravity itself. Once any object, a planet, a spaceship, or even a particle of light crosses this threshold, its fate is sealed. The escape velocity, the speed needed to break free from the black hole's gravitational pull, exceeds the speed of light. Since nothing in the universe can travel faster than light, nothing can ever come back out. From the perspective of an outside observer, the event horizon is where the laws of physics as we understand them seem to take a leave of absence. If you were to watch a friend foolishly pilot a ship toward a black hole, you'd witness something truly strange. As their ship approached the event horizon, the incredible gravitational pull would cause the light coming from them to stretch out, shifting to longer and longer wavelengths. This effect, called gravitational redshift, would make their ship appear to fade from view, becoming redder and dimmer until it seemingly vanishes entirely. To you, it would look as if your friend had frozen in time, forever suspended just at the edge of the horizon, their image eternally stretched and fading but never quite disappearing completely. But for your friend inside the ship, the experience would be entirely different and far more terrifying. They wouldn't feel a sudden jolt or pass through a dramatic barrier. The crossing would be uneventful, a smooth transition with no flashing signs or physical sensations to mark the moment. However, the view out their window would transform into the most bizarre sight in the cosmos. As they crossed the horizon, the entire universe behind them wouldn't just appear distorted. It would seem to collapse into a single, blindingly bright circle of light directly behind them, containing all of cosmic history compressed into a single point. Ahead of them, only pitch blackness. They are now cut off from the rest of existence, sailing into a region of space where every possible path leads inexorably toward the singularity at the center. The event horizon is the final curtain, and once it falls, there is no encore. But this bizarre distortion of light and fate is just a prelude to an even more profound effect. The immense gravity of a black hole doesn't just trap light. It warps the very fabric of space-time so severely that it alters the passage of time itself. This phenomenon, predicted by Einstein's theory of general relativity, is known as time dilation, and near a black hole's event horizon, its effects are pushed to the absolute extreme. To understand how this works, let's step away from the cosmic abyss for a moment and consider a more familiar concept: gravity's influence. We often think of gravity as a force that simply pulls us down, but Einstein revealed it is actually a curvature in the four-dimensional fabric of spacetime. The stronger the gravity, the more spacetime is curved and the more time itself is forced to slow down. This isn't just a theoretical idea, we measure it every day. The GPS satellites orbiting Earth, for instance, experience slightly weaker gravity than we do on the surface. Because of this, their clocks actually run faster by a tiny fraction of a second each day. If engineers didn't constantly correct for this effect, the entire system would become useless within minutes, giving you driving directions that are miles off. This proves that time dilation is real and measurable, even here in our own neighborhood. Now, amplify that effect by a factor of billions. As you approach a black hole, the gravitational field becomes unimaginably intense. To an observer watching from a safe distance, your clock would appear to tick slower and slower the closer you get to the event horizon. If you could hover just above that boundary, your time would virtually grind to a halt from their perspective. For every single minute you experienced in that incredible gravity, years, decades, or even centuries could be passing for everyone else in the universe. Imagine a pair of twins. One boards a powerful ship and journeys to orbit a black hole, while the other remains on Earth. The traveling twin might experience what feels like a few hours of flight near the event horizon. But when they finally break away and return home, they could find that their Earth-bound sibling has aged decades, and the world they left behind is utterly unrecognizable. They wouldn't have traveled through space so much as they would have traveled into the future. This has stunning implications for the theoretical possibility of interstellar travel. A journey to a distant star might normally take tens of thousands of years, making it utterly impractical. But by using the gravity well of a black hole as a time machine, a crew could potentially make the trip in what subjectively feels like a short period. The catch, of course, is that there would be no returning to the era they came from. Everyone they ever knew would be long gone. They would become permanent exiles from their own time. This isn't just science fiction. It's the hard truth of physics, revealing that time is not the universal, constant beat of a drum we perceive it to be, but a fluid, malleable river that flows at different rates throughout the cosmos, rushing fastest of all in the deep, gravitational valleys carved by these dark giants. And if you thought the sheer density and gravity of a black hole was impressive, just wait until you learn that many of them are also spinning. We tend to picture these cosmic objects as static, silent traps, but the reality is far more dynamic. When a massive star collapses to form a black hole, it holds onto much of its original angular momentum, the same property that causes a figure skater to spin faster when they pull their arms in. Imagine that star millions of miles across, spinning perhaps once every few weeks. Now, crush all of that immense mass down into a singularity. To conserve that spinning motion, the resulting black hole must rotate at a truly staggering rate, often spinning hundreds of times every single second, with its outer edges approaching the speed of light. This rapid rotation doesn't just make for an interesting fact, it fundamentally warps the structure of the black hole and the space around it. A non-spinning or Schwarzschild black hole has a perfectly spherical event horizon and a point like singularity at its center. But a rotating black hole, known as a Kerr black hole after the physicist who discovered the solution, is a much more complex and fascinating beast. The incredible centrifugal forces generated by the spin flatten the black hole, much like a spinning pizza dough bulges at the middle, creating a shape called an oblate spheroid. The event horizon itself actually shrinks slightly compared to a non-spinning black hole of the same mass. But the most dramatic effect happens just outside the event horizon in a region called the ergosphere. This is an oval-shaped region of space that is dragged around by the black hole's rotation like a cosmic riptide. Within the ergosphere, it is literally impossible for anything to remain stationary. Space-time itself is being pulled around so forcefully that you would be compelled to move with it, no matter how powerful your spaceship's engines. This isn't just a gravitational effect. It's a testament to how a rotating black hole twists the very fabric of the universe around it. The ergosphere also presents a theoretical gold mine. Because objects can enter this region and still escape, advanced civilizations might one day harness this dragged space to extract enormous amounts of energy, a process known as the Penrose process, by dropping matter into the ergosphere and collecting the energy released. The spin also changes the nature of the singularity itself. Instead of a single, infinitely dense point, many models suggest the rapid rotation stretches the singularity into a ring, a one-dimensional loop with zero thickness but finite diameter. This ring singularity is thought to have even more bizarre properties, potentially acting as a gateway to other universes or other points in space-time, though this remains firmly in the realm of theoretical speculation. Ultimately, a spinning black hole is a much more accurate representation of what likely exists in our universe, showing us that these objects are not simple, static holes but dynamic, energetic engines that actively sculpt the spacetime around them with their incredible rotational power. This profound evaporation, however, leads us directly to one of the most heated debates in all of modern physics, a paradox so deep it threatens to unravel our understanding of reality itself. It's called the black hole information paradox, and it pits two of our most successful theories, quantum mechanics and general relativity, against each other in a fundamental clash of cosmic principles. To understand the paradox, we first need to understand what physicists mean by information. It's not like a book or a digital file. In quantum mechanics, information refers to the complete quantum state of every single particle. It's the unique identity card of every electron and quark, its mass, its charge, its spin, its velocity. The core tenet of quantum theory is that this information can never be truly lost or destroyed. It can change form, it can get scrambled and mixed up with other information, but it must always be preserved in some way. If you could somehow reverse all the laws of physics, you should, in theory, be able to trace the history of the universe backward and reassemble every particle exactly as it was. Information, in this sense, is eternal. Now bring a black hole into the picture. Let's say you throw something into it, something with a vast amount of information, like a detailed encyclopedia set. According to Einstein's general relativity, that information is gone. It has crossed the event horizon and is irretrievably lost to the universe, destined to be crushed into the singularity. The black hole itself only remembers three things about whatever it swallows: its total mass, its electric charge, and its angular momentum. Everything else, all the intricate details that made that encyclopedia a unique collection of information, is erased. This presents no problem for classical physics. The paradox emerges from Stephen Hawking's own discovery. If a black hole evaporates over eons through Hawking radiation, what finally happens to all that information that fell in? Hawking's initial calculations showed that the radiation leaking out is entirely random, purely thermal. It contains no trace of the information about the particles that formed the black hole or that fell in later. It's like burning a book. The heat and light given off tell you nothing about the words that were printed on its pages. So, if the black hole completely evaporates, leaving behind only this random, featureless Hawking radiation, then the information it once contained has been permanently erased from the universe. This violates the most sacred rule of quantum mechanics. Physicists have been wrestling with this for decades, and several potential solutions have been proposed. One intriguing idea is that the information isn't actually lost at all. Perhaps it is somehow encoded on the surface of the event horizon itself before the material ever falls through, a concept known as the holographic principle. It suggests that all the three-dimensional information about an object is smeared into a two-dimensional representation at the boundary, like a complex hologram. Then, as the black hole evaporates, this information could be slowly and subtly imprinted onto the Hawking radiation that escapes, ensuring it is returned to the universe in a vastly scrambled but complete form. Another, more radical possibility is that black holes don't completely vanish. Maybe evaporation stops at a certain point, leaving behind a tiny, stable remnant no bigger than a particle, but containing within it the compressed information of everything it ever consumed. This microscopic relic would be a fossil of cosmic history. The debate is far from settled, and resolving this paradox is likely the key to unlocking a deeper, unified theory of quantum gravity, finally bridging the gap between the world of the very small and the realm of cosmic giants. It's easy to get so focused on the incredible pull of a black hole that we forget what happens outside the event horizon. While the singularity is the ultimate destination for anything that crosses the point of no return, not everything that approaches a black hole actually falls in. In fact, some of the most spectacular and consequential cosmic events occur in the dynamic, chaotic region just beyond the grip of the event horizon. Far from being simple destroyers, black holes also act as some of the universe's most powerful and efficient recyclers, taking in matter and blasting it back out in a transformed state, seeding the galaxy with the ingredients for new life. This incredible process is driven by the accretion disk, a swirling, superheated maelstrom of gas, dust, and stellar debris that forms as material is pulled in by the black hole's gravity. Think of it as a cosmic whirlpool where friction and immense magnetic fields heat the material to millions of degrees, causing it to glow brighter than all the stars in a galaxy combined. But this isn't just a one-way trip into the drain. The physics within this disk are so violent and energetic that not all of the incoming material is doomed. Through processes we are still working to understand, a portion of this superheated plasma is focused and accelerated by the black hole's powerful magnetic fields, launching it away from the poles at nearly the speed of light. These are relativistic jets, and they are among the most powerful phenomena in the known universe. These jets can extend for hundreds of thousands of light years, far beyond the boundaries of their host galaxy, acting as intergalactic fire hoses that inject immense energy and newly forged elements back into the cosmos. The material within these jets isn't just random debris, it's enriched with heavy elements like iron, oxygen, and carbon, the very building blocks of planets and life. These are elements that were forged in the hearts of stars and during supernova explosions, now being gathered by the black hole and launched back out into the emptiness of intergalactic space. In this way, a black hole is not an endpoint but a transformative engine. It takes the remnants of dead stars, subjects them to the most extreme conditions imaginable, and then propels them outward where they can eventually cool, condense, and become part of new molecular clouds. This has a profound effect on the future of the galaxy itself. When these jets slam into the vast clouds of gas that float between stars, they compress them. This compression can be the trigger that causes these clouds to collapse under their own gravity, igniting the birth of new stars and planetary systems. It's a beautiful and violent cycle of cosmic death and rebirth. The same force that destroys stars and consumes light also, paradoxically, creates the conditions for new stars to form and for rocky, metal-rich planets like Earth to eventually coalesce. The iron in your blood, the calcium in your bones, and the oxygen you breathe were all likely spread across the galaxy by the explosive death of a star, and some of those very atoms may have once been part of a magnificent jet fired from a black hole millions of years ago. They are the ultimate recyclers, ensuring that even in death, the material of the universe is never wasted, but instead is used to build anew. To truly grasp the staggering scale of these cosmic behemoths, let's bring the comparison a little closer to home. We've talked about supermassive black holes, but there exists an even more extreme category, the ultramassive black hole. These are the true titans of the void, with masses that dwarf even the impressive supermassive class, reaching well beyond 10 billion times the mass of our Sun. Their scale is so immense, so far outside our everyday experience, that it defies intuitive understanding. One of the most effective ways to comprehend it is to use our own solar system as a measuring stick. Consider the familiar path of our planets. Neptune, the most distant major planet from the Sun, orbits at an average distance of about 2.8 billion miles. The vast sphere of space enclosed by its orbit defines the classical boundary of our solar system. Now, take an ultramassive black hole like the one powering the quasar-ton 618, which is estimated to be a staggering 66 billion times more massive than our Sun. The event horizon of such a monster, the point of no return, is not a compact sphere. It is an abyss so wide that its diameter is approximately 13 times larger than the entire width of Neptune's orbit. Our entire solar system, from the fiery heart of the Sun to the icy, distant Kuiper belt objects, would fit comfortably inside that black sphere with room to spare. The Earth, the other planets, and every comet and asteroid would all be orbiting well inside the event horizon. their fates sealed long before they were ever spaghettified or torn apart. This isn't just a hypothetical scenario for distant galaxies, it's a reality in our own cosmic backyard. The supermassive black hole at the center of the Milky Way, Sagittarius, a star, is relatively placid now, but its event horizon is still enormous. With a mass of 4 million suns, its Schwarzschild radius, the radius of its event horizon, is about 7.3 million miles across. That's roughly 17 times the distance from the Earth to the Moon. While our entire solar system wouldn't fit inside it, the orbits of Mercury, Venus, Earth, and Mars would all be completely engulfed. This perspective shifts the black hole from a distant curiosity to a dominant architectural feature of our galaxy, a gravitational anchor whose silent presence dictates the motion of hundreds of billions of stars, including our own Sun, which continues its endless journey around this unseen dark heart. While the image of a lone black hole silently drifting through space is a powerful one, the universe is a dynamic and often violent place, and even these gravitational titans are not immune to dramatic encounters. In the dense cores of galaxies or within tight star clusters, two black holes can find themselves locked in a gravitational dance, slowly spiraling toward one another until they collide in one of the most energetic events since the Big Bang itself. This merger is not a simple blending, but a spectacular celestial tango that fundamentally reshapes the cosmos and sends ripples across the very fabric of space-time. The process begins over millions of years. If two black holes are born from a binary star system or are drawn together in a crowded region of space, they will start to orbit one another. As they whirl around their common center of mass, they lose energy by distorting the space around them, emitting what are known as gravitational waves. These are ripples in the fabric of spacetime itself, predicted by Einstein over a century ago. Initially, this energy loss is tiny and the in-spiral is slow. But as the black holes get closer and their speeds increase, the process accelerates dramatically. In the final, frantic minutes before the collision, they can be orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. The space around them becomes a chaotic storm of distorted gravity. Then, in a fraction of a second, they merge. Their two distinct event horizons stretch, merge, and settle into a single, larger black hole. But the new black hole is initially a lopsided, vibrating mess, and it must shed this excess energy to assume its final, calm, spherical form. It does so in a final, tremendous burst of gravitational waves, releasing more energy in that instant than all the stars in the observable universe combined emit in light over the same period. For that brief moment, the merging black hole becomes the most powerful source of gravitational radiation in the cosmos, a flash of invisible energy that propagates outward at the speed of light. For decades, this incredible phenomenon existed only in theory and computer simulations. That all changed on September 14, 2015, when a team of scientists at the Laser Interferometer Gravitational Wave Observatory, or LIGO, made a discovery that would earn them a Nobel Prize. Their incredibly sensitive instruments, which work by measuring tiny changes in the distance between mirrors caused by a passing gravitational wave, detected a signal unlike any other. It was the signature chirp of two black holes, one about 36 times the mass of the Sun and the other 29, merging over 1 billion light-years away. The signal was faint, distorting the 4-kilometer long arms of the LIGO detectors by a distance 10,000 times smaller than the diameter of a proton, but it was unmistakable. For the first time in history, humanity had directly observed gravitational waves and heard the cosmic thunderclap of a black hole merger. This event, designated GW150914, didn't just confirm a key prediction of Einstein's theory, it opened an entirely new window on the universe. Before this, our view of the cosmos was entirely based on light from visible waves to radio and X-rays. But now we can listen to the universe through the vibrations of space-time itself. This is the era of gravitational wave astronomy, and it allows us to study the dark universe, probing events that emit little to no light, like the collisions of black holes and neutron stars. Each new detection adds to our catalog of these mysterious objects, helping us understand how they form, find each other, and ultimately come together in some of the most spectacular and fundamental processes governing the evolution of our universe. But what if everything we've just described about a black hole, the event horizon, the point of no return, the perfect cosmic cloak, wasn't an absolute rule? What if, under certain extraordinary circumstances, that cloak could be ripped away, exposing the naked, unfiltered singularity to the rest of the universe? This isn't just a wild science fiction scenario. It's a serious, though highly controversial, theoretical possibility known as a naked singularity. In our standard picture, the event horizon acts as a crucial protective barrier. It's a one-way curtain that forever separates the bizarre, lawless physics of the singularity from the orderly universe we inhabit. This idea is so central that physicists often refer to it as cosmic censorship, a poetic way of saying that nature, in its wisdom, seems to hide these infinite, physics-breaking anomalies from our view to preserve the predictable rules that govern everywhere else. The singularity is censored, its infinite density and gravity kept safely behind the event horizon where it can't wreak havoc on causality and physics. A naked singularity would be the ultimate violation of this principle. Imagine a gravitational point of infinite density just hanging out in space, with no event horizon to shield the cosmos from its immense and paradoxical influence. You could, in theory, fly a spaceship right up to it, observe it directly, and then fly away to tell the tale. You wouldn't be trapped because there would be no point of no return to cross. The sheer existence of such an object would throw modern physics into a state of profound crisis. The implications are staggering. For one, it would force a complete rewrite of general relativity, as our current equations break down catastrophically at a singularity. Being able to observe one directly would provide the first ever laboratory for studying quantum gravity, the elusive theory meant to unite Einstein's relativity with quantum mechanics. We could finally see what happens to matter, space, and time under the most extreme conditions imaginable. Furthermore, the causal nightmares that the event horizon prevents would become terrifyingly real. With a naked singularity, you could potentially have closed time-like curves, effectively creating paths that travel backward in time and opening the door to all the paradoxes that come with it, like meeting your own grandfather before you were born. The big question, of course, is whether such an object could actually form. Some complex mathematical models, particularly those involving the collapse of a rapidly spinning star or one with an unusual distribution of mass, suggest it might be possible for a singularity to form without an event horizon. However, most physicists believe that some unknown law of quantum gravity would always intervene to prevent this cosmic indecency, either by stopping the collapse just short or by forming a horizon at the last instant. To date, we have no observational evidence for a naked singularity, and they remain one of the most tantalizing and disruptive ideas in theoretical physics, a ghost in the machine that promises either a revolution in our understanding or a confirmation that the universe truly does believe in keeping its most dangerous secrets safely locked away. But if you think the jets from a typical supermassive black hole are impressive, they are merely candles next to the cosmic lighthouse of a quasar. These are not just the most energetic phenomena in the universe, they are the absolute brightest, most violent, and most powerful engines we have ever observed. A single quasar can outshine an entire galaxy of hundreds of billions of stars, and the secret to this staggering power lies in the ravenous appetite of a supermassive black hole operating at its absolute limit. The term quasar is actually a shortening of quasi-stellar radio source, a name given in the 1960s when these objects were first identified. Astronomers pointed their telescopes at what appeared to be faint, star-like points of light, but were baffled to discover they were emitting enormous amounts of radio waves. Their true nature was even more shocking. By analyzing their light, scientists realized these weren't stars in our own galaxy at all. They were incredibly distant, meaning their light had traveled for billions of years to reach us. To appear so bright from such a mind-boggling distance, they had to be producing almost unimaginable amounts of energy. The only possible engine powerful enough to explain this is a supermassive black hole in a state of extreme gluttony. Picture a black hole at the center of a young galaxy, surrounded by a vast, dense reservoir of gas, dust, and even entire stars. As this material spirals inward, it doesn't fall in smoothly. It forms an accretion disk of such immense scale and ferocity that it defies belief. The friction within this disk heats the gas to temperatures of millions of degrees, causing it to glow with intense ultraviolet and X-ray light. The conversion of gravitational energy into light and heat in this process is breathtakingly efficient, up to 40 times more efficient than the nuclear fusion that powers stars. The black hole is essentially acting as the ultimate gravitational generator, and the luminosity is so intense that it can blow the surrounding gas clear out of the galaxy, effectively shutting down star formation in the region. This is the heart of a quasar, a supermassive black hole actively feasting. The incredible brightness comes from the very edge of the event horizon, the last place where light can still escape before being lost forever. The most powerful quasars are thought to be consuming the equivalent of 10 to 1,000 Earth masses of material every single minute. This constant, violent influx of matter is what lights the fuse, creating a beacon so brilliant it can be seen across the vast expanse of the observable universe. They are cosmic artifacts from a more violent era, when galaxies were young and fuel for their central black holes was abundant. Studying them is like looking back in time, giving us a direct window into the chaotic and energetic processes that helped shape the galaxies we see in the more sedate modern universe. For all our talk of distant quasars and merging giants, we have our very own supermassive black hole right here in the galactic neighborhood. Nestled deep within the constellation Sagittarius, 26,000 light-years from Earth, lies Sagittarius, a star, the 4 million solar mass anchor of our Milky Way galaxy. Its discovery is a testament to human curiosity and ingenuity, a decades-long detective story that pieced together clues from the chaotic core of our own island universe. For years, astronomers noticed something strange about the center of the Milky Way. Radio telescopes detected a powerful, compact source of radio waves emanating from that direction, which they named Sagittarius A. But the real breakthrough came when scientists began meticulously tracking the orbits of individual stars in that crowded region. Using powerful adaptive optics on telescopes like the Keck Observatory in Hawaii and the Very Large Telescope in Chile, they were able to cancel out the blurring effects of Earth's atmosphere and watch these stars dance over years and decades. What they saw was breathtaking. These stars were whipping around an invisible point at speeds of thousands of miles per second, making sharp, elliptical orbits that could only be explained by the gravitational pull of an incredibly massive, incredibly compact object. By precisely charting the orbit of one star in particular, known as S2, they calculated the mass of the invisible anchor, roughly 4 million times the mass of our Sun, all contained within a space smaller than the orbit of Mercury. The only possible explanation was a supermassive black hole, and Sagittarius, a star, was its name. Unlike the brilliant quasars of the early universe, our galactic center is relatively quiet, a sleeping giant. But quiet is a relative term. While it's not actively consuming vast amounts of material and shining with incredible brilliance, it is far from inactive. Observations in infrared and X-ray light reveal that Sagittarius, a star, is a restless sleeper, occasionally flaring and flickering as it snacks on small clouds of gas and dust that venture too close. These outbursts can cause its brightness to increase by 100-fold in just a few minutes, a dramatic sign of the violent processes still at play just outside the event horizon. Scientists are keenly studying these flares to understand the physics of accretion, how material finally falls across the point of no return in real time. The most stunning confirmation of its nature came in May of 2022, when the Event Horizon Telescope collaboration, the same team that brought us the first image of the black hole in M87, released an image of our own galactic center. It wasn't a clear, crisp photo of the black hole itself, of course, but a brilliant, glowing ring of light surrounding a dark shadow, the telltale signature of superheated gas swirling around the event horizon of Sagittarius, a star. This image, a monumental achievement built from data gathered by a virtual Earth-sized telescope, provided the most direct visual evidence possible that this massive object is indeed a black hole. It's like getting a family portrait of the most mysterious member of our galactic household, confirming its identity beyond any doubt. Studying this relative cosmic neighbor gives us an unparalleled laboratory to understand the behavior of supermassive black holes up close, teaching us how they influence their surroundings and ultimately how they shape the evolution of galaxies like our own. Now, let's turn our attention to one of the most profound mysteries in all of modern cosmology: dark matter. We know it's out there. We can see its gravitational influence holding galaxies together and bending the light from distant stars, but we have never directly detected a single particle of it. It makes up about 85% of all the matter in the universe, yet it remains completely invisible, a ghostly presence that has eluded scientists for decades. But what if the answer to this cosmic riddle has been hiding in plain sight? What if dark matter isn't made of some exotic, unknown particle, but is instead composed of the oldest and most elusive black holes in the universe? This is the fascinating premise behind the primordial black hole theory. Unlike the stellar mass black holes formed from dying stars or the supermassive ones at galactic centers, primordial black holes are thought to be ancient relics, forged in the extreme conditions of the universe's first second of existence. Imagine the cosmos in its infancy, a seething, dense, and incredibly hot soup of energy and fundamental particles. In such a chaotic environment, tiny but intense fluctuations in density could have caused regions of space to collapse under their own gravity directly, without needing a star to die first. These wouldn't be the massive giants we've discussed. They could range in size from smaller than a single atom to larger than a star, each one a tiny knot of infinite density born from the raw energy of the Big Bang. The beauty of this idea is its simplicity. It offers an elegant solution to two major puzzles at once: the nature of dark matter and the origin of black holes that existed before the first stars were even born. If vast numbers of these primordial black holes were created and then scattered throughout the universe, they could be drifting through galaxies right now, including our own Milky Way. Because they don't emit light and only interact with their surroundings through gravity, a widespread population of them would be virtually invisible, yet their combined mass would perfectly explain the gravitational effects we attribute to dark matter. They would be the ultimate cosmic ghosts hiding in the darkness between stars, their collective pull guiding the motion of galaxies and shaping the large-scale structure of the universe itself. Of course, a theory this compelling faces serious challenges and requires careful fine-tuning. If too many small primordial black holes were created, their eventual evaporation through Hawking radiation would have left behind a specific signature of radiation that we do not observe. Furthermore, their gravitational lensing effects, where their gravity bends the light from background stars, would be detectable, and while we have seen a handful of candidate events, there haven't been enough to account for all dark matter. This has led many scientists to propose that it might be a specific mass range of primordial black holes, perhaps those with masses similar to a large asteroid or even a planet, that could have survived to the present day and evaded detection, collectively making up the missing mass of the universe. It's a cosmic detective story of the highest order, And while the case isn't closed, the possibility remains that the darkest secrets of the cosmos are held not by unseen particles, but by countless ancient black holes born in the fire of creation. But this idea of a one-way journey into a black hole naturally leads to a tantalizing question. What if the story doesn't end at the singularity? What if there's a way out? This brings us to one of the most fascinating and speculative ideas in all of theoretical physics, the white hole. If a black hole is the ultimate cosmic drain, a region of space where anything can fall in but nothing can escape, then a white hole would be its exact opposite, a hypothetical fountain, a point in the universe where matter and energy spontaneously erupt outward, but where nothing can ever enter. It's a concept that emerges not from direct observation, but from the elegant and often bizarre mathematics of Einstein's field equations. The equations of general relativity, which so perfectly describe the curvature of spacetime around a black hole, are time-symmetric. This means that if you take the mathematical solution for a black hole and literally reverse the direction of time in the equations, you get the solution for a white hole. It's the theoretical time reversal of a black hole's life cycle. Instead of a relentless gravitational collapse, you get an explosive, irresistible outburst. The event horizon of a white hole would still be a one-way boundary, but in reverse, you could leave, but you could never, ever cross back inside. It would be like a movie of a black hole running backward, with all the consumed matter and energy being violently vomited back out into the universe. The appeal of this idea is instantly obvious. It offers a potential resolution to the uncomfortable finality of the black hole singularity. Perhaps a black hole doesn't just crush everything into an infinite point of no return. Maybe it acts as a tunnel, a wormhole, connecting our region of spacetime to another, with the white hole being the exit point in a different time or even a completely different universe. In this stunning scenario, the material that falls into a black hole in our cosmos could be the very material that creates a new, baby universe of its own, with the white hole serving as its Big Bang. It's a beautiful, cyclical vision of cosmology, where the death of matter in one realm gives birth to an entirely new reality. However, for all its mathematical elegance and science fiction appeal, the existence of white holes in our universe faces monumental physical hurdles. The second law of thermodynamics, which states that entropy, or disorder, always increases, seems to stand in direct opposition to their formation. A white hole erupting from a perfectly ordered singularity would represent a massive decrease in entropy, effectively making it appear as if time were running backward. Furthermore, for a white hole to form, it would have to somehow exist in a state of perfect isolation from the very beginning of time. If even a single particle of dust from our universe were to fall into it, the entire delicate mathematical structure would collapse back into a black hole. Essentially, our universe is far too messy and filled with matter for a pristine white hole to survive for more than an instant. While they remain a captivating playground for theorists, pushing the boundaries of what might be possible in the fabric of spacetime, no astronomical object we have ever observed possesses the properties of a white hole, leaving them, for now, as one of the most intriguing and profound what-ifs in our understanding of the cosmos. For decades, the conventional wisdom in physics was beautifully simple, if a bit austere. It was summed up by the elegant no-hair theorem. This idea, championed by icons like John Wheeler, suggested that black holes are the ultimate simpletons of the cosmos. No matter how complex, unique, or messy an object is when it falls in, be it a glittering diamond, a library of books, or an entire star, the black hole that results is stripped of all those details. According to this theorem, a black hole can be completely described by just three, and only three, properties: its mass, its electric charge, and its spin. That's it. Everything else, every intricate detail that made the fallen material unique, is lost forever behind the event horizon, erased from the universe. The name no hair is a metaphor for this lack of any other distinguishing features or hair. A black hole is essentially bald with no complicated frills or textures. But what if this elegant simplicity is a little too clean? What if black holes, in their own mysterious way, actually hold onto a memory of what created them? This is where one of the most intriguing challenges in theoretical physics comes into play. The no-hair theorem is a product of classical general relativity, but our universe isn't just classical, it also obeys the bizarre rules of quantum mechanics. When physicists began trying to reconcile these two worlds in the context of black holes, they hit upon the information paradox, which we discussed earlier. If information cannot be destroyed, then the no-hair theorem, which insists that information is destroyed, must be incomplete. This paradox sparked a revolution, leading some scientists to propose that black holes might in fact have a subtle form of hair after all. This isn't hair you could see or comb. It's not a physical substance. Instead, think of it as an incredibly faint, complex imprint, a quantum signature etched onto the surface of the event horizon itself. This quantum hair, as it's often called, would theoretically preserve information about the material that fell into the black hole. Imagine throwing a perfectly symmetrical rubber ball into a pool of water. The splash and the ripples it creates are unique to that ball. Its size, its weight, the angle it entered. In a similar, though infinitely more complex way, the gravitational field of a black hole might contain faint ripples or imprints that encode the properties of the objects that formed it or that have since fallen in. It would be a cosmic fingerprint, a hidden record of the black hole's history. The search for this quantum hair is at the very frontier of physics. Researchers are developing sophisticated mathematical models to understand how this information could be preserved without violating the fundamental laws of relativity. Some theories suggest that the event horizon might be able to store information in its structure, like a hologram where a three-dimensional object is encoded on a two-dimensional surface. Finding evidence for this would be a monumental breakthrough, solving the information paradox and providing our first real glimpse into how gravity and quantum mechanics unite. It would transform our view of black holes from simple, destructive pits into complex cosmic entities that, in their own unique way, remember everything they have ever consumed. This profound connection between the birth of the universe and the darkest objects within it brings us to one of the most captivating ideas in modern cosmology. What if the very first black holes didn't have to wait for the lives and deaths of massive stars? What if they were born in the fire of creation itself, emerging from the unimaginable energy and density of the universe's very first moments? These hypothetical objects are known as primordial black holes, and they are thought to be ancient relics, potentially formed not from dying stars but from the raw chaos of the Big Bang. To understand how this could happen, we need to rewind the cosmic clock to a time before the first stars, before the first atoms, even before the first stable particles. In the initial fraction of a second after the Big Bang, the entire universe was an incredibly hot, dense, and turbulent soup of energy and fundamental forces. In such an extreme environment, tiny random fluctuations in density were happening everywhere. Most of these ripples were minor and smoothed themselves out. But in some regions, the density might have been so intensely high that the force of gravity won out over the outward pressure of the expanding cosmos, causing a tiny pocket of space to collapse directly into a black hole. It wouldn't require a star's core collapse. It would be a direct birth from the energy of the infant universe itself. The potential size of these primordial black holes is one of their most fascinating aspects. Unlike their stellar mass cousins, they wouldn't be constrained by the mass of a collapsing star. They could theoretically be almost any size. Some might have been microscopic, with masses less than a speck of dust but compressed into a space smaller than an atom. Others could have been as massive as a planet or even a star, all formed within the first second of existence. Their size would have been determined by the scale of the density fluctuation that created them. a larger over-dense region would have collapsed into a more massive black hole. The existence of these ancient objects isn't just a curious footnote. It could solve several major cosmic puzzles at once. For one, as we touched on earlier, they are a compelling candidate for dark matter. If the early universe produced a vast number of relatively small, asteroid-mass primordial black holes, they would be drifting through our galaxy completely unseen, their collective gravitational pull perfectly explaining the mysterious force that holds galaxies together. Furthermore, some astronomers speculate that these primordial black holes could have acted as seeds for the supermassive black holes we see at the centers of galaxies today. How did those giants get so big so fast? It's a much easier problem to solve if they started out as sizable primordial black holes, giving them a massive head start on accumulating more material over billions of years, rather than having to grow from scratch from a single stellar corpse. The hunt for these elusive relics is ongoing and ingenious. Since a small, dense object would bend light, astronomers look for a phenomenon called microlensing. If a primordial black hole were to pass directly between us and a distant star, its gravity would act like a lens, briefly focusing the star's light and causing it to appear to brighten for a short period before fading back to normal. Surveys that monitor millions of stars have seen a handful of these unexplained microlensing events, but not yet enough to confirm a widespread population. Another method involves listening for the final farewell of the smallest ones. A primordial black hole with a mass around that of a large asteroid would be reaching the end of its life through Hawking radiation right about now. Its evaporation would culminate in a spectacular burst of high-energy gamma rays, a flash that observatories like NASA's Fermi Gamma Ray Space Telescope are constantly watching for. Finding one would be like discovering a living fossil from the dawn of time, a direct messenger from the universe's first second of existence, offering us a unique window into conditions so extreme that no other probe could ever hope to reach them. And that idea of a white hole as a cosmic fountain of creation brings us to one of the most breathtaking and mind-expanding hypotheses in all of cosmology. What if every black hole in our universe isn't an end but a beginning? What if the gravitational collapse of a star doesn't just create a singularity, but actually births an entirely new universe with its own laws of physics and its own cosmic timeline? This isn't just science fiction, it's a serious, though highly speculative, theory proposed by physicists like Lee Smolin, and it suggests that our entire cosmos might itself be the offspring of a black hole in a parent universe. To understand how this could be possible, we have to reconsider what happens at the very center of a black hole. Our current physics breaks down at the singularity, but it's possible that this isn't a true point of infinite density. Instead, it might represent a boundary, a point where the equations of our universe stop being valid and a new set of physical laws takes over. In this scenario, the immense energy and matter crushed into the singularity don't just vanish. They are reborn in an explosive event that, from the inside, looks exactly like a Big Bang. The black hole's event horizon from our perspective becomes the point of origin for an entirely new space-time continuum, expanding into its own dimensions, completely separate and disconnected from our own. This leads to a staggering vision of reality known as cosmological natural selection, or the fecund universe theory. It paints a picture of a multiverse that evolves. In this model, universes reproduce. A universe that contains stars which live, die, and form black holes is a universe that is fertile, capable of spawning countless child universes. Each of these new universes might have slightly different fundamental constants, perhaps a slightly stronger gravitational force or a different value for the speed of light. Most of these offspring would be stillborn or incapable of forming stars and atoms, but occasionally, by random chance, a child universe would have the perfect settings to allow for the formation of stars, galaxies, and crucially, more black holes, making it fertile and able to continue the cosmic lineage. This theory offers a potential and deeply elegant answer to one of the most perplexing questions in science. Why is our universe so perfectly fine-tuned for life? The constants of nature seem improbably perfect. If gravity were even slightly stronger, the universe would have collapsed back on itself immediately after the Big Bang. If it were slightly weaker, stars and galaxies never would have formed. The fecund universe theory provides a mechanism for this fine-tuning, natural selection. Over countless generations, universes that are good at making black holes, which require stable stars and the right physical laws, are selected for. We find ourselves in a universe that is ideally suited for making black holes because that's exactly what it was selected to do. The existence of life, which depends on those same precise constants, is almost a happy byproduct of this cosmic reproduction cycle. The implications are truly humbling. It means that every black hole we observe could be a separate universe in its own right, a whole cosmic expanse existing within a singularity that, from our outside view, is smaller than an atom. Our entire universe, with its hundreds of billions of galaxies, might be contained within a black hole that exists in a vastly larger parent universe. This creates a cosmic family tree of unimaginable scale, with our universe being just one branch in an infinite fractal of creation. While this remains a speculative hypothesis without direct evidence, it transforms the black hole from a symbol of ultimate death into a potential cradle of new life, a cosmic womb where the laws of physics are reborn and the cycle of existence continues forever. And yet, for all their terrifying power and destructive potential, there exists a stunning loophole in the physics of a black hole, a scenario so counterintuitive it seems plucked from science fiction. It is the one exception to the rule of immediate and gruesome death, and it all depends on the black hole's immense scale. While falling into a typical stellar mass black hole would spell instant doom, crossing the event horizon of a supermassive black hole could theoretically be an event an astronaut might not only survive but initially fail to even notice. The key to this bizarre possibility lies in the strength of tidal forces, which we discussed earlier in the context of spaghettification. Remember, it's not the overall strength of gravity that tears you apart, but the difference in gravity's pull between one part of your body and another. For a smaller black hole, the event horizon is very close to the singularity, meaning the gravitational gradient is incredibly steep. The difference in pull between your head and your feet is catastrophic and immediate. However, a supermassive black hole is an entirely different beast. Because its mass is distributed over such a colossal volume, its event horizon is located much, much farther from the central singularity. The gravitational pull at the event horizon is still strong enough to trap light, but the change in that pull over the distance of a human body is far more gradual, far less extreme. Imagine the difference between walking off a cliff and descending a ramp. The cliff represents a small black hole, a sudden, fatal drop. The ramp represents a supermassive black hole, a gentle, sloping grade. For an astronaut falling toward a black hole like Sagittarius, a star, with its event horizon stretching over 7 million miles wide, the tidal forces at that boundary would be remarkably mild. You could cross this ultimate threshold without feeling a sudden jerk, without hearing a dramatic sound, and without your body being immediately stretched into a stream of particles. From your perspective inside your spacecraft, the crossing would be completely uneventful, a non-event marked by no physical sensation at all. This doesn't mean your fate isn't sealed, it absolutely is. But your perception of the journey would be profoundly strange, governed entirely by the warping of spacetime. As you fell inward, the view outside your window would become the most distorted sight in the cosmos. The universe behind you wouldn't just shrink, it would appear to collapse into a single, brilliant circle of light directly above you, containing all of cosmic history compressed into a shrinking disk. Ahead of you, only an abyss of perfect blackness, and while you might survive the crossing itself, the inevitable pull toward the singularity remains. Deeper inside, far from the event horizon, the tidal forces would eventually begin to grow, starting the fatal process of spaghettification. But for a brief, surreal window of time, you would be alive inside a black hole, a witness to physics pushed to its absolute limit, traveling toward a destiny that lies forever hidden from the outside universe. This profound warping of gravity is so intense that it doesn't just trap light. It sculpts the very paths that light can travel, transforming the black hole into the universe's most powerful natural telescope. This incredible phenomenon is known as gravitational lensing, and while it occurs around any massive object like a galaxy or a star, the effect around a black hole is pushed to its most extreme and dramatic limit. The gravity of a black hole is so overwhelming that it creates a deep, steep well in the fabric of space-time, causing any light ray passing nearby to fall into that gravitational valley and have its path bent dramatically. Imagine space-time as a taut, flexible rubber sheet. Placing a bowling ball in the center creates a noticeable dip, and rolling a marble near it will cause the marble to curve around the bowling ball. Now replace that bowling ball with an impossibly dense, infinitely heavy lead weight that stretches the rubber sheet into a near-vertical funnel. That is the space-time curvature around a black hole. When light from a distant star or galaxy travels through this severely warped region, it doesn't travel in a straight line as we expect. It follows the curves of this distorted space-time, its path bent and twisted by the black hole's incredible gravity. This isn't a minor deflection. The bending can be so extreme that the light from a single object behind the black hole can be smeared, duplicated, and magnified. From our viewpoint on Earth, this means we might see multiple images of the same distant quasar or galaxy, stretched into faint, luminous arcs or rings encircling the dark silhouette of the black hole itself. This effect, called an Einstein ring when it forms a complete circle, is a perfect demonstration of his theory of general relativity in action. The black hole acts as a cosmic lens, its gravity focusing the faint light from objects so far away they would normally be impossible for our telescopes to see, effectively giving us a magnified view of the distant universe. Astronomers actively use this principle to peer deeper into space than ever before. By carefully studying the distortion and magnification caused by a black hole or even a massive galaxy cluster warping the light from objects behind it, they can map the distribution of dark matter, discover extremely distant galaxies, and test the predictions of relativity under the most extreme conditions. It's a perfect example of how the most destructive forces in the cosmos can also serve as invaluable tools for discovery, using the warped space around a black hole to illuminate the darkest and most distant corners of our universe. But how do we even know these invisible giants are out there in the first place? We can't see them directly, so their discovery relies on a cosmic game of gravitational detective work. And some of the most compelling evidence comes from watching the intimate dance between a black hole and a seemingly ordinary star. Far from being isolated monsters, many black holes are part of binary systems, locked in a gravitational embrace with a stellar companion. It's by observing the frantic, telltale wobble of these visible stars that astronomers can infer the presence and even calculate the properties of their invisible dark partners. This method of discovery is beautifully straightforward in principle. For centuries, we've understood that two massive bodies orbit a common center of mass. When one partner is far more massive, like the Sun is to Earth, that center of mass lies deep within the larger object. But when the two objects are more comparable in mass, they both make noticeable orbits around a point in the space between them. Now, imagine one of those objects emits no light whatsoever. To a distant astronomer, the system would look utterly bizarre. A single, visible star seemingly pirouetting around an empty point in space, compelled by the gravity of an unseen master. This isn't just a theoretical idea, it's how the first stellar mass black hole candidate, Cygnus X1, was identified. Astronomers were tracking a brilliant blue supergiant star, and they noticed its light rhythmically shifting between blue and red. This Doppler shift indicated the star was regularly moving toward us and then away from us. It was orbiting something. By calculating the speed and period of its orbit, they could determine the mass of the object pulling it around. The result was staggering. The invisible companion had to be at least 15 times the mass of our Sun. Yet they could see nothing. The only object that could be that massive, that compact, and that dark was a black hole. The star's lonely dance was the signature of a cosmic phantom. These binary systems are far more than just a way to find black holes. They are incredible natural laboratories. By studying the orbit, we can precisely measure the black hole's mass. If the system is also a source of X-rays, it tells us something even more exciting. The black hole is actively feeding. In many of these pairs, the black hole's powerful gravity is actively pulling gas away from its companion star. This stolen material doesn't fall in straight down. It spirals inward, forming a superheated accretion disk that glows brilliantly in high-energy X-rays before vanishing across the event horizon. Monitoring these X-ray flares and flickers gives us a real-time look at the extreme physics of accretion, how matter behaves in the most intense gravitational fields imaginable. These duos also reveal the diverse life cycles of black holes. Some have companion stars that are slowly being consumed, while others may have orbits that are gradually decaying as they lose energy to gravitational waves destined for a future merger. Each system is a unique case study, a snapshot of a relationship between a star and the darkest object in the universe, providing invaluable data that helps us understand how these mysterious entities form, evolve, and influence their surroundings. They are a perfect example of how sometimes, to see the invisible, you simply have to watch the visible things being pulled by its force. This idea of a faint, cold glow from the event horizon leads us to one of the most counterintuitive and fascinating facts about these cosmic objects. Black holes have a temperature. We typically think of them as the ultimate cold, dark voids, but thanks to Stephen Hawking's groundbreaking work, we now understand that they are not completely black. They emit a faint thermal radiation, and with emission comes heat, and with heat comes a measurable temperature. This isn't a temperature you could feel like the warmth of the sun. It's an incredibly subtle phenomenon, but its existence completely redefines our understanding of these gravitational giants. The temperature of a black hole is inextricably linked to its mass, and the relationship is perfectly inverse. The more massive the black hole, the colder it is. A typical stellar mass black hole, say 10 times the mass of our Sun, would have a temperature of a minuscule fraction of a degree above absolute zero, colder than anything we can naturally find in the universe today. To put it in perspective, this temperature is about 1/6 millionth of a Kelvin. Now consider a supermassive black hole like the one at the center of our galaxy. With 4 million solar masses, its temperature plummets to about 1/10 millionth of that already unimaginably cold value. These objects are not just cold, they are among the coldest theoretical objects in existence. This creates a fascinating cosmic competition. The universe is not a perfect void. It is filled with the faint afterglow of the Big Bang, known as the cosmic microwave background radiation. This relic radiation has a steady temperature of about 2.7 Kelvin, a persistent warmth that permeates all of space. For any black hole with a temperature colder than this, which is every known black hole in the current universe, the cosmic background radiation is actually warmer. This means these black holes are, on a net balance, absorbing more energy from the universe than they are emitting through Hawking radiation. They are slowly, imperceptibly, gaining mass from the faint heat of creation itself. They won't begin the process of net evaporation until the universe has expanded and cooled far beyond its current state, trillions upon trillions of years from now, when the background temperature finally drops below their own. For now, even as they slowly leak radiation, they are growing colder in an ever-cooling universe, waiting for the distant future when they will finally begin to shine. Yet this paradox, this fundamental clash between our two most successful theories of reality, may not be the final word. In recent years, a potential solution has been gaining traction, one that is as elegant as it is mind-bending. It suggests that the information isn't lost at all. It's never actually allowed past the event horizon in the first place. Instead, it is meticulously preserved, encoded on the two-dimensional surface of the black hole's boundary like a cosmic hologram. This is the holographic principle, and it could be the key to resolving one of physics' greatest dilemmas. To grasp this, we need to shift our perspective on the event horizon. We usually think of it as a one-way door, but the holographic principle proposes it acts more like an incredibly high-resolution film projector. Imagine you want to project a perfect three-dimensional image of an apple onto a screen. You wouldn't need a real apple behind the projector. You would just need the right two-dimensional data on the film itself to create the convincing illusion of a three-dimensional object for anyone viewing it. The holographic principle applies this same idea to the entire universe. It suggests that all the information needed to describe a three-dimensional volume of space, like everything inside a black hole, can be fully encoded on its two-dimensional boundary, the event horizon. When an object falls in, its information isn't crushed into the singularity. Instead, it is translated into a complex, scrambled pattern on the surface of the horizon, a kind of quantum fingerprint imprinted at the point of no return. This leads to a stunning implication. The event horizon is not a passive boundary but an active, information processing surface. Theoretical work, particularly by physicists like Leonard Susskind, suggests that this surface is composed of minuscule, vibrating bits of spacetime, each one Planck length in size. When anything falls into the black hole, it disturbs these bits, causing them to vibrate and store the information about the fallen object in an incredibly dense and complex way. The three-dimensional reality we perceive inside the black hole is, according to this view, a projection from the data stored on this two-dimensional surface. The fallen object is both inside the black hole and simultaneously smeared across its outer skin. The final piece of this puzzle addresses how the information eventually gets out. Hawking radiation, once thought to be purely random and thermal, is now believed by many to carry the imprint of this horizon-stored information. As the black hole evaporates over eons, the Hawking radiation particles that escape are not random. They are subtly correlated with the information encoded on the horizon. It's an incredibly complex and slow process, like watching a book being shredded and then having its confetti thrown into a hurricane. But in principle, the information is all still there. If you could collect all the Hawking radiation the black hole ever emitted and had a sufficiently powerful quantum computer, you could, in theory, unscramble it and reconstruct the complete history of everything that ever fell in. The information is returned to the universe, not destroyed, solving the paradox and preserving the core rule of quantum mechanics. While the mathematics behind this is exceptionally complex and the debate continues, the holographic principle offers a beautiful and profound vision of a universe where information is truly eternal, and even the darkest objects play by the rules. But if you thought the influence of a black hole was limited to its immediate surroundings, think again. These gravitational powerhouses don't just consume matter, they can also become the universe's most powerful slingshots, capable of flinging entire stars across the galaxy at speeds so incredible they can never return. These aren't your average stars drifting peacefully through the cosmos. These are hypervelocity stars, and they are some of the fastest solitary objects we have ever discovered, racing through the void at millions of miles per hour. This incredible process begins with a simple but powerful principle of orbital mechanics, the gravitational slingshot effect. We've used this technique ourselves with space probes like Voyager, gently stealing a tiny bit of momentum from a planet to boost a spacecraft's speed. But near a supermassive black hole, this interaction is anything but gentle. Imagine a binary star system, two stars locked in a tight mutual orbit that has the misfortune of wandering too close to the galactic center. The immense gravity of the supermassive black hole can violently disrupt this partnership. In a complex three-body gravitational tug-of-war, one of the stars can be captured into a tight orbit around the black hole, while its companion is flung away at an astonishing velocity like a stone from a catapult. The energy for this incredible launch doesn't come from nowhere. It's siphoned directly from the orbital energy of the black hole and the captured star. The result is a star that isn't just moving quickly, it's moving fast enough to achieve escape velocity from the entire galaxy. We're talking about speeds that can exceed 2 million miles per hour. At that rate, you could travel from Earth to the Moon in less than 15 minutes. These hypervelocity stars become cosmic outcasts, their trajectories carrying them on one-way trips out of the Milky Way and into the vast, empty intergalactic medium. The first of these stellar speedsters was discovered in 2005, a massive blue star hurtling through space at over 1.5 million miles per hour. Since then, we've found dozens more, each one a testament to a violent encounter in the distant past. Their paths often trace back directly to the galactic center, pointing to Sagittarius, a star, as the likely culprit. Studying these stars gives us a unique opportunity to understand the dynamics of the chaotic environment around supermassive black holes. They act as cosmic forensic evidence, allowing us to reconstruct dramatic events that happened millions of years ago. Furthermore, by measuring their composition and velocity, we can even map the gravitational potential and the distribution of dark matter throughout our galaxy, using these accidental projectiles as probes to illuminate the darkest secrets of the Milky Way. They are a breathtaking reminder that in the cosmic dance of gravity, destruction and creation are often two sides of the same coin, and even a star's tragic exile can become a valuable tool for discovery. Yet for all their colossal scale and ancient origins, some of the most revolutionary black holes in the universe might be hiding in a form so small it defies imagination. We've journeyed through the realm of stellar giants and supermassive monarchs, but there exists a theoretical frontier at the opposite extreme of size, the microscopic black hole. These hypothetical entities would be smaller than an atom, yet they could hold the keys to unlocking the universe's deepest secrets, from the existence of extra dimensions to the fundamental unification of all physics. The concept arises from a fascinating interplay between quantum mechanics and gravity. According to some calculations, if you could compress any amount of mass, even just a few grams, into a space small enough, known as its Schwarzschild radius, it would collapse into a black hole. For an object the mass of Earth, that critical size is about the width of a marble. For a human being, it's smaller than a single proton. And for a microscopic black hole, we're talking about masses that could be as small as a mountain or even a speck of dust, all compressed into a space a million times smaller than a single atom. Under the normal laws of physics as we understand them, creating such an object requires energies and pressures far beyond anything we can achieve, energies reminiscent of the first moments after the Big Bang. This is where our most powerful machines enter the story. When the Large Hadron Collider was first powered up, a flurry of public concern emerged that it might accidentally create a tiny black hole that could sink into the Earth and consume our planet from within. While this made for dramatic headlines, physicists were quick to reassure the public that this scenario was firmly in the realm of science fiction. According to Einstein's general relativity, the energy required to create even the tiniest black hole is astronomically high, far beyond the reach of any collider we could build. Any microscopic black hole created under these standard rules would evaporate into a puff of Hawking radiation in an unimaginably short instant, lasting far less than a trillionth of a second and posing no threat whatsoever. However, the story takes a dramatic turn when we introduce one of the most exciting ideas in theoretical physics: string theory and the possibility of extraspatial dimensions. Our everyday experience is confined to 3 dimensions of space and 1 of time, but string theory, an attempt to unite gravity with quantum mechanics, suggests there could be many more dimensions of space, perhaps 10 or 11 in total, that are curled up and hidden from our view, too tiny for us to perceive. If these extra dimensions exist, they could fundamentally change the strength of gravity on the smallest scales. In our 3-dimensional world, gravity is remarkably weak. It's the feeblest of the 4 fundamental forces. But if it were allowed to leak into these other dimensions, its true strength could be revealed only at incredibly small distances. This possibility opens the door for the Large Hadron Collider to become a black hole factory after all. If gravity is amplified on these tiny scales due to extra dimensions, then the energy required to create a microscopic black hole could plummet to levels within the collider's reach. In this scenario, the violent collision of 2 protons could, for a fleeting moment, create a concentration of energy so dense that it warps the fabric of spacetime across all dimensions, briefly knitting together a tiny, transitory black hole. It would be an incredible sight, not a planet-devouring monster, but a subatomic wonder that would instantly evaporate in a unique shower of particles, leaving behind a distinct signature in the detectors. Discovering such an event would be arguably the most significant breakthrough in physics since the dawn of quantum mechanics. It would provide the first direct, experimental evidence for the existence of extra dimensions, confirming a central prediction of string theory and forever altering our understanding of reality's basic structure. It would also offer us a tiny, controllable laboratory for studying quantum gravity, allowing us to observe how gravity behaves when it's combined with the quantum world in a way we can never do with a cosmic giant. We could test Hawking's radiation theory directly and probe the conditions of the very early universe. While the hunt continues and no such event has been confirmed, the mere possibility that our largest machines could unveil the smallest black holes is a breathtaking testament to human curiosity, showing that the keys to the cosmos's greatest mysteries might be hidden not only in the vastness of space, but also in the infinitesimal depths of reality. And this gravitational influence extends far beyond just a few wayward stars, reaching out to shape the very destiny of the galaxy itself. We often picture black holes as cosmic vacuum cleaners, but their true role is far more nuanced and profound. They act as the ultimate regulators, the unseen architects that determine whether a galaxy will be a vibrant nursery of new stars or a quiet, aging retirement home. This incredible process, known as feedback, is a delicate cosmic balancing act between creation and destruction, and it's one of the most active areas of research in modern astrophysics. It begins with that superheated accretion disk. When a supermassive black hole actively feeds, it doesn't do so quietly. The immense friction and powerful magnetic fields within the disk don't just create light, they generate colossal outflows of energy. Think of it as a cosmic engine that has 2 exhaust pipes. The first are those relativistic jets we discussed, focused beams of particles and radiation screaming away from the poles at nearly light speed. The second is a more general, explosive wind of high-energy particles and radiation that blasts outward in all directions. This isn't a gentle breeze, it's a hurricane of energy that pushes against the surrounding gas and dust throughout the galactic center. This energetic outburst creates a powerful feedback loop. That vast reservoir of gas is the very fuel for future star formation. For stars to be born, giant clouds of this gas need to cool down, collapse under their own gravity, and ignite fusion. But the radiation and winds from the active black hole heat the gas, preventing it from cooling and collapsing. It's like trying to build a snowman next to a blazing bonfire. The raw material is there, but the environment is too hot for it to stick together. In this way, the black hole acts as a cosmic thermostat, switching off star formation in the central regions of the galaxy. This self-regulation is crucial. Without it, a galaxy could theoretically consume all of its gas in a frantic burst of star formation, burning out quickly and leaving behind a dead relic. The black hole ensures a more measured, sustainable evolution, but the story doesn't end with simply shutting things down. This feedback is also creative. Those immense jets and winds can sweep up vast amounts of gas, compressing it into dense shells at their leading edges. While the inner region is heated and cleared out, these outer compressed layers can actually trigger a new wave of star formation, like a cosmic plow turning over soil and planting new seeds. Furthermore, by preventing a single, rapid burst of star birth, the black hole helps to extend the galaxy's life, allowing it to form stars over billions of years rather than in a single, brief and furious epoch. The supermassive black hole is not just a destroyer, it is a master sculptor using its incredible power to carve, heat, and compress the material of its galaxy, ultimately dictating its structure, its pace of life, and its long-term evolution in an intricate dance of cosmic feedback. For centuries, black holes existed as phantoms in the equations of physicists' powerful predictions that we could only infer from their gravitational influence on the cosmos. We could chart the orbits of stars whipping around an invisible point. We could measure the X-rays screaming from superheated gas, but the black hole itself remained a silhouette, a theoretical shadow we could never directly see. All of that changed on April 10, 2019, when a team of scientists unveiled an image that made history, the first direct visual evidence of a black hole's event horizon. This wasn't an artist's impression or a computer simulation. It was a real photograph, a monumental achievement that transformed these cosmic mysteries from abstract concepts into observable reality. This revolutionary breakthrough was the work of the Event Horizon Telescope, or EHT, which is less a single telescope and more a telescope of planetary scale. The challenge is immense. Taking a picture of a black hole is like trying to photograph a DVD on the surface of the moon. To achieve this impossible resolution, astronomers used a technique called very long baseline interferometry, which essentially turns the entire Earth into a giant radio dish. They synchronized 8 of the world's most powerful radio observatories, from the high deserts of Chile to the frigid peaks of Hawaii and the South Pole, to all observe the same target at the exact same time. The precision required is almost beyond belief. Each telescope collected waves of light, and the data was stamped with time signals from atomic clocks accurate to within 1 second every 100 million years. This data was then physically shipped on hard drives far too vast to transmit over the internet to central processing centers where supercomputers combined it all. The process is akin to having a single Earth-sized mirror. The larger a telescope's mirror, the finer the detail it can resolve. By combining signals from telescopes scattered across the globe, the EHT achieved an angular resolution unmatched by any instrument in human history. For over a week in April of 2017, all 8 telescopes stared relentlessly at 2 primary targets: the supermassive black hole at the heart of galaxy M87, 55 million light-years away, and our own Sagittarius, a star. The data they gathered was so colossal that it took years of meticulous analysis and calibration to piece together the final image. The result was a glowing, fiery ring of light surrounding a distinct dark shadow, the unmistakable signature of a black hole. That now iconic image of the M87 black hole reveals far more than just a pretty picture. It is a treasure trove of scientific confirmation. The bright ring isn't the event horizon itself, but the photon ring, superheated gas and dust swirling around the black hole at nearly the speed of light, just outside the point of no return. The light is brighter on one side because of the Doppler effect. The material moving toward us at relativistic speeds appears brighter, while the material moving away appears dimmer. The dark central region is the black hole's shadow, a region about 2.5 times larger than the actual event horizon. This shadow is created because the black hole's immense gravity bends light paths so severely that it captures any photon that gets too close, creating a dark void in the center of the brilliant emission. The size and shape of this shadow perfectly match the predictions of Einstein's theory of general relativity for a black hole of that mass and spin, providing yet another stunning validation of his century-old ideas under the most extreme conditions imaginable. While the M87 image captured the public's imagination, the subsequent release of an image of our own galactic center, Sagittarius A star, in May of 2022 was arguably an even greater technical feat. Though it is 2,000 times closer to us than M87, it is also over 1,000 times less massive and therefore has material orbiting it much faster, causing its appearance to change on timescales of mere minutes. Capturing a clear image was like trying to take a sharp photograph of a puppy chasing its tail. The EHT team had to develop sophisticated new algorithms to average out this frantic motion and reveal the persistent underlying structure, which, stunningly, also showed that familiar glowing ring and central dark shadow. Seeing our own local gravitational monarch confirmed beyond any doubt was a profound moment, making the vast and abstract cosmos feel intimately connected to our own place within it. The EHT project has flung open a new window on the universe, initiating the era of direct black hole observation. Future plans involve adding more telescopes to the array, including space-based observatories, to create an even larger virtual dish and achieve even sharper images. We will move from still photos to movies, watching in real time as gas clumps orbit the event horizon and as the black hole's shadow flickers and changes. This will allow us to directly probe the dynamics of spacetime itself, testing the laws of physics in a regime where they have never been tested before. The first image was the end of a decades-long quest, but it was truly just the beginning, the opening shot in a revolutionary new chapter of astronomy, where we can finally stare directly into the heart of darkness and begin to understand its secrets. As we've journeyed through these 30 astonishing facts, it becomes clear that black holes are so much more than the terrifying voids of popular imagination. They are not merely cosmic destroyers, they are fundamental architects of the universe, crucial to its structure, its evolution, and perhaps even its very existence. Each fact peels back a layer, revealing a deeper truth that challenges our most basic assumptions about reality. We've seen how they warp time, stretch matter, and trap light, but we've also discovered their creative power, seeding galaxies with the elements for life, regulating the birth of stars, and possibly even birthing entirely new universes. They are the ultimate paradox, points of infinite density that can also be fountains of creation, objects of profound darkness that illuminate our understanding of physics. This exploration fundamentally changes our perspective. The universe is not a static stage where events simply unfold. It is a dynamic, interconnected, and deeply mysterious place where the most extreme conditions forge the rules that govern everything. Black holes are the key that unlocks this reality. They force us to merge the world of the very large, described by Einstein's relativity, with the realm of the very small, ruled by quantum mechanics. In their shadows, we find the clues to a grander, unified theory of everything. They teach us that space and time are not rigid and separate, but are a flexible, woven fabric that can be bent, twisted, and perhaps even tunneled through. They show us that information, the very essence of reality, might be eternal, preserved on a boundary we once thought was a one-way door to oblivion. This new view transforms our place in the cosmos. We are not just distant observers of these magnificent events, we are products of them. The iron in our blood, the calcium in our bones, was likely forged in the heart of a star and may have been spread across the galaxy by the powerful jet of a black hole. We are living in a galaxy shaped and anchored by a silent, supermassive giant at its core. By understanding black holes, we ultimately understand more about our own origins and our own home in this vast, expanding reality. They are the ultimate teachers, showing us that the universe is far stranger, more wonderful, and more interconnected than we ever dreamed. We've covered an incredible amount of ground, from the terrifying spaghettification at the event horizon to the mind-bending possibilities of white holes and new universes. Now, we want to hear from you. Which of these 30 facts completely reshaped your perspective? Was it the revelation that you could theoretically survive crossing the event horizon of a supermassive black hole? The idea that they might be the mysterious dark matter, or perhaps the beautiful notion that every black hole could be the seed of an entirely new cosmos? Let us know in the comments below. We read every single one and love hearing what sparks your curiosity about this amazing universe we all share. If your sense of wonder is as ignited as ours is, make sure you don't miss out on our next journey into the cosmos. We're always exploring new mysteries, from the depths of neutron stars to the secrets of dark energy. Hit that subscribe button and tap the bell so you never miss an upload. Thank you so much for watching, and never stop looking up.